Thank you for the introduction. Okay. This is a presentation about improving and automating a BFV parameter selection with an average case approach. It's a paper that we recently wrote with Chiara, Marco, and Johannes. And the motivation of the work has born from a practical need of our team. We needed to use FHE in a project, and we faced the challenge of the parameter selection. The problem of the parameter selection in FHE schemes in general depends on the noise growth. And in particular, there is an error introduced for security reason during the encryption phase, and it grows as homomorphic operations are performed. In particular, it grows exponentially with multiplications. In order to guarantee correctness, the ciphertext modulus has to be very large, and this creates a problem decreasing the security level of the schemes. And for this reason, to re-increase the security level, we have to enlarge the polynomial degree, which usually has a big cost in the efficiency. Our aim is to find an effective analysis of the noise growth, so to tighten the bounds on the ciphertext modulus for correctness. The contribution of our paper is an average case studio for the error growth in the BFV schemes, in the BFV scheme, which is the first one. And it should have been an easy task, but in the end, it turned out to be quite intricate because of the multiplication. Indeed, the variance is not just the product of the variance of the errors or the previous errors multiplied by n, because there is not an independence assumption that it was there in the other schemes. So we had to introduce a correcting function to fix this problem. Moreover, we computed some closed formulas for the bounds in generic circuits, and we propose an interactive tool for the parameters generation, which extends the work of Mono and others on BGV. It combines the security formula with our new theoretical results. The state of the art about the BFV parameter selection was based on the canonical norm, which has some kind of conservative bounds usually, and average case approaches were proposed for other schemes like TFHE, CKKS, and BGV. Regarding the automation of the parameter selection, there had been mainly two works. Bergerat and others proposed a framework for efficiently selecting parameters in TFHE-like schemes, and Mono and others developed an interactive parameter generator for the BGV schemes that supports arbitrary circuit models. Okay, now I will introduce the FV scheme, focusing on the problem related to the error. I would start saying that in some notation. So the security of the scheme is based on the ring learning with error problem, in particular on its decisional version, which is the following. We sample A, which is a polynomial. These polynomials are from this ring, so the integer ring modulus f of x, where f is a monic irreducible polynomial. In particular, in FV, we have f of x, which is x to the n plus 1, with n, which is a power of 2. We sample this polynomial with the coefficients in minus q half q half, errors from an error distribution, and in particular a secret, an unknown S randomly. This unknown is fixed, while we can take pairs of the form A and B, where B is computed as in this way. And the problem is distinguishing these pairs from random ones. This problem is considered to be intractable. So this is again the ring learning with error problem, and I will show how some instances are used in the key generation and encryption to ensure security. So in the key generation, we sample A from the uniform distribution on RQ. We sample a secret S from a key distribution. In our case, it will be a ternary distribution. And we sample an error E from the error distribution. The secret is S, while the public key is AB, which is an instance of the RLWE problem. In the same way, the security is guaranteed on the ciphertext generation, on the encryption. We have the decryption, which is the following. It is correct because if we study this quantity, we have that from the rounding of Q divided by Tm, we obtain this quantity. And then the other terms delete, and we only have some small errors. And from the first element, we get M, then some error, which is included in this bclean, and then we have some polynomial multiples of T. If we consider the decryption, it is the following. So we have that this K per T term deletes by this modulo Q, and the rounding doesn't involve M. So we have a correct decryption if we get M, which is when all the coefficients of the polynomial bclean belong to this interval. We studied the distribution of the coefficients of the polynomial bclean, and we saw that computationally that they are well approximated by identically distributed Gaussians, whose average is 0, and the variance is the following. If we bound the variance with this quantity, 1/8 d to the 2, we have that the probability that the decryption is correct is the following, which is overwhelming already when we set d like 6 for the usual values of n, which are around the 2 to the 12 to 2 to the 15. The error keeps being like that also after the homomorphical operation. We give a generic characterization. In particular, we call invariant noise the minimum, as Ilyashenko defined in his thesis, the minimal nu, such that this equation holds for k, which is an integer polynomial. And we still have that every time this error can be well approximated by an identical distributed Gaussian, its coefficients, with mean 0. And so the same probabilistic bound holds for the variance being bounded by this quantity. We can also write the error always like a sum of terms we call the iota and power of S. And the variance, because of some characteristic of these terms, can be computed in this way. In the following, I will show without details how does the error change and how does the variance change in the main operations. So we have given two ciphertext computed independently. We have that the errors are this v and nu and nu prime of this form. We consider S to be a fixed vector, but it has its coefficient have mean 0 and variance Vs. In this way, we have the two errors independent. When we do an addition, the two errors are summed, and so are the variance of the coefficients. And in the same way, with the modulus switch, we have that to the error is added another error, which is this VMS, depending on the of QL prime, which is the new ciphertext modulus. And this new quantity is independent of nu. So the variance can be computed at the sum of the two variances. And in particular, we have that the second term is of the form BMS divided by, this should be Q to the second, where BMS doesn't depend on Q prime. In the multiplication, we have this big error. We try to compute the variance as follows, considering the coefficients of the polynomial independent among each others. And we obtain this formula, but we discovered that the result were an underestimation of the true ones. And the reason is that instead, when we compute the variance of the error of the multiplication coefficient, it is multiplied by this power of S. I just wrote a term because it was a bit too long, but it gives the idea. So the power of S here, it's iota 1 plus iota 2, while when we just multiply the two variances, we have the product of these two sums, which is not the same. So we tried to estimate the ratio between the two. To get a simple formula to try to estimate from the easy one with the independent coefficients, a simple formula for the true variance. We started analyzing computationally the particular case when one of the powers is 1, and this quantity can be well approximated by a function which we called f of this form, so -1 divided by e to the a iota minus b plus c. This a, b, c depend only on the ring dimension, and we computed it with Python function curveFit. I give an example in the figure. With this function, we exploit it to create a new function, which is g, which is the product of f of I from 0 to iota. And f of 0 and 1 is 1, it's defined as 1, while f for e bigger than 2 is the previous find. By induction, we can prove that the sum of this sum can be approximated by this other quantity, so n Vs, which is the variance of the coefficients of the key, to the power of iota multiplied by g of iota. It follows that the variance of the multiplication error coefficient, which is this term with this sum, can be approximated by the other term multiplied by this g of iota 1 plus iota 2 divided by g of iota 1 multiplied by g of iota 2. Moreover, we can give a bound on this quantity, this ratio with g, which is this one, where t was the maximum power of s, which was in the errors. So we can we have this we have that the variance becomes smaller than the previous quantities, but multiplied by this term. And so we have a final easy formula for the computation, which is the easy one with these terms more. Moreover, we give a further simplification, because the first and the last terms are negligible compared to the others, and this depends on the fact that the variance of an error, including the variance of the multiplication for the scheme to be correct has to be smaller than 1 divided by 8 d to the 2, and so also the single summands in this equation have to be, and so we have that the first term has to be very small because of this, and so it's negligible too, and we have this new formula. We use it in computing the variance. The variance of the error in a easy circuit. In particular, we consider a circuit when we do at addition and then one multiplication, and then again at addition and one multiplication for how many times we need. We have that the variance of one level changes as follows. So we have this quantity eta, which depends on the additions, and then all the others that depends on the multiplication. And in particular, we have this f, which was our correcting function, and we get that we can write it as in this way, and exploit this to find recursively the final variance, which is the biggest, because we always add new terms or multiply by this term, which is much bigger than 1. So the only bound that we need is this VL1, which has to be less or equal than 1 divided by 8d to the 2. In particular, all these terms can be written as this constant, and we have q only in the denominator as a q to the 2 and nowhere else. So we can give a bound on q to the 2, which is the following. I cannot go further. Okay. Okay. We show some results. In particular, we compared our results with the previously obtained with the canonical norm, and we also compared them to the experimental ones that we found with the OpenFHE library. We use for the comparison, to make it more clear, the noise budget, which is kind of how much is missing from for filling all the bits allowed. So we can see already from this, we have that the can means that it's the result with the canonical norm. Our is the one that we had, and exp is the one from the experiments. And we also, it's a bound on the maximum value. We also present the mean value experimental. We have that already in the encryption, addition and multiplication. There are some differences. So we have better bounds than with the canonical norm and pretty close to the experimental ones. The results are even better when we consider base circuits of depth just 2 or 3, and we do eta addition with eta equal to 8. So we can see that the bound is much better compared to the canonical norm, but still pretty close to the other one. And these results also in much better estimation of the ciphertext modulus Q. This is the ciphertext theoretical estimation. We present it with we present a log 2 of Q, and the difference is quite big. Finally, we implemented the parameter generator, which is available on GitHub. It is implemented in Python, and it extends the work of Mono and others on BGV to BFV using their security formula and our results. It gives code snippets to use directly on the libraries, and it's implemented in particular for OpenFHE. And that's all. Thank you.
Okay, thank you very much for that, Beatrice. It was a very interesting talk. We have some questions already in the chat. Florent, do you want to unmute and ask your question?
Okay, I can read it then.
Yes, sure. Yes, first, thank you for the very interesting talk. It's very nice to see this analysis. So yes, the question I have, maybe a very simple one, is so how much of this analysis can be carried over to other schemes such as BGV or SKKS? For instance, if I want to do a similar analysis for CKKS, would I need to redo the whole analysis, or are some intermediate results that you obtain usable for these other schemes?
Sorry, I cannot understand many of the words. I think it's a bit disturbed.
Yes, sorry, my connection is not great. Yes, so my question is how much of this analysis can be extended to other schemes such as BGV or CKKS?
I don't know CKKS. BGV can be similar. I'm not sure about that.
Okay, thank you.
Okay, so next we have a question from Nigel.
Hi, yeah, could you put your slides back up? Hold on, let me even show myself there. Okay, can you put your slide back on for like number 19 or something like that? Yeah, slide 19. One of the tables anyway, just so yeah.
This one?
Yeah, that one. No, the previous one. I'll get to that one. It was 18, then 19. Yeah, so just the previous one, or any of the. Yeah, so something like that. So, I think I've misunderstood something, because these are the bounds on the noise, yeah?
These are the bounds of the maximal value that the error can reach.
The error can reach, okay, right. But your maximum value is less than your mean value.
It's because we are using the noise budget, which is like the opposite, because it's minus logarithm of 2 of
Aha, okay. So a big value here means a small value of the actual noise.
Yeah, exactly.
Right, okay. So just so I really understand what you're talking about, because this then flew through me at the very end. Okay, so what you're saying is that your noises are less than you would get with the canonical norm.
Yes.
Yeah, and therefore on slide 19 you have smaller parameters.
Yes.
Tick. Okay, right. I now understand. Okay, that was the thing that confused me. Thank you very much. It was a great talk, apart from my idiot and misunderstanding at the end. Thank you.
Thank you.
Okay, and there's one more question from Bhuvnesh. Bhuvnesh, do you want to unmute and ask your question? If not, I'll read the question for people on YouTube. So the question is, as per my understanding, oh, sorry, Bhuvnesh.
Yeah. Yes.
Go ahead.
Yeah, hi, Beatrice. So my question is that, as per my understanding, your work is kind of related to estimating the noise or a bound of the noise that is the resultant of some homomorphic computation. So my question is actually like the kind of security implications that this kind of work might lead to. So because there has been a recent attack in literature where the adversary can use a bound of this noise value to kind of perform a binary search to retrieve the final error value from some certain ciphertext. So do you really think that this kind of work might lead to make the
Yeah, I'm not sure I understood, but I think that having a smaller ciphertext modulus should have a smaller impact on the security. Like we don't need a bigger n the polynomial degree to have the same security. It should be better.
My real question was, suppose I can use your method to kind of get to know the bound of the final error value or a certain range where the final error value might lie. So in that case, there was a recent work where the attacker shows that the author shows that an adversary can use this bound to kind of perform a binary search to extract the final error value from a certain ciphertext. So do you think that your work might make the life of this adversary a bit easier?
I don't think I understood. I'm sorry.
Okay. Okay, that's fine.
Maybe we can follow up on the Discord with a discussion on that question. Any more questions? Don't be shy. No, okay, well, if not, then I'm sure I speak for everyone when I say thank you very much, Beatrice, for taking the time today to present to us. It was a very interesting talk, and thank you for your time. Just as a reminder to everyone to join the Discord, I will drop that into the chat. Right. It's going in the chat. And yeah, as per usual, the resources will go onto YouTube and fhe.org within the week, so that everybody can benefit from today's talk. So yeah, again, thank you everyone for joining us. Until the next meetup, have a good week, and we'll continue with our post-session coffee break for 5 minutes or so, just to have a little chat without the recording. So if anyone wants to hang around for a chat, feel free.
Thank you.